Hello everyone, this is the presentation of our paper entitled Prediction of Reward Function for Deep Reinforcement Learning via Gaussian Process Regression. This work has been done by researchers in Machine Learning and Control Systems Laboratory in Yonsei University, Seoul, South Korea. Let us start from the concept of reinforcement learning. The goal of reinforcement learning is to find an optimal policy which maximizes the expectation of the discounted sum of the rewards. In recent years, a large amount of attention has been paid in estimating the reward functions of the reinforcement learning from experts' demonstration, as a framework of inverse reinforcement learning. Inverse reinforcement learning aims to find an expert's reward function from given demonstration, by assuming the expert demonstrations were performed by the optimal policy subject to its own reward function. Imitation learning through end-to-end training needs to consider all possible situations because the agent may show an unexpected behavior when encounters unconsidered situations. On the other hand, inverse reinforcement learning can give us more sufficient solution than an end-to-end training. This method can be applied to user-specific AI such as autonomous driving system with user-specific driving behavior, and also can be used for animal or human behavioral studies. Here is our question. Can we apply inverse reinforcement learning methods to the complex real-world robot applications? In real-world robot application, the number of expert demonstrations is often insufficient to recover the reward function, because it is normally expensive to collect. And the robot may use high-dimensional sensory measurements from vision sensor, depth camera, or LiDAR, which commonly used in the autonomous driving vehicles. In early studies, inverse reinforcement learning algorithms were designed to handle discrete states and actions. To handle continuous states and actions, recent inverse reinforcement learning works approximate reward, policy, and action value functions using deep neural networks, but these networks update simultaneously and the update of the neural networks affects each other. The learning process may be difficult to be stabilized. These problems may worsen if the system stability depends on the reward function. Moreover, high-dimensional observation space requires more number of weight parameters of deep neural networks. It finally requires more number of data sets. To resolve those problems, we proposed an efficient way to solve inverse reinforcement learning problem based on Gaussian process regression with L1 regularization. This idea is based on an interpretation that there is some functional relationship between a set of possible reward functions and a set of possible trajectories. The algorithmic flow of the proposed method is as follows. First, the reward functions are sampled from a set of possible reward functions. Then trajectories corresponding to each of reward functions are generated by policies trained by a deep reinforcement learning algorithm. And the trajectory reward pairs are used to train GP. Finally, trained GP can predict a reward function of an expert when a small set of expert trajectories are given. To validate the proposed inverse reinforcement learning method, we considered an obstacle avoidance navigation to a given target of a mobile robot. The robot can detect the surrounding obstacles by LiDAR measurement, and the robot can estimate its current pose by calculating the odometry and measuring the IMU. The proposed approach requires a parameterization of the reward function. We parameterized the reward function by a reward feature, f. Delta D gives the positive reward when the robot getting close to the target. R avoid penalizes getting too close to the surrounding obstacles. R curvature is proportional to the square of the robot turning rate, derived from time optimality of the robot navigation task. In summary, F is the scalar penalty gain for collision in the reward function. We assume the reward parameter f as a realization by a Gaussian process with the input variable x, which is extracted from the trajectory zeta. The expert reward function can be obtained by predicting the expert reward feature, and the prediction is equal to the conditional expectation given the data pair, D. The data pair, D, will be generated from sampled reward functions and its corresponding optimal trajectories. To generate the data pair D, we sampled reward parameters uniformly. In the simulation environment, autonomous navigation trajectory of the mobile robot is generated by the policy which is trained by deep reinforcement learning algorithm given reward function with sampled reward parameter. For the simulation environment, we used VREP simulator from Capalia Robotics. The sequences of sensory measurements, robot poses, control inputs in robot trajectories are high-dimensional data and have a nonlinear dependencies, which makes it difficult to apply regression directly. Thus, we extracted the features from those sequences. We extracted 9 features from each trajectory. 3 features are extracted in the manner of modified Hausdorff distance metric. Next 6 features are extracted in terms of the time optimality. However, each feature is calculated by different calculation methods. Now we have the input data X by extracting the features from the trajectories, but we don't know which feature is important or not. We took the idea of the feature selection from lasso regression, we applied L1 regularizer to our GP. This approach allowing us to select the important features for the decision process of the expert. To regularize GP with L1 norm of the hyperparameter vector, we replaced length scale hyperparameters of the squared exponential kernel with regression coefficients W. Now we can estimate GP hyperparameter with new objective function, which is negative log marginal likelihood plus L1 regularization term. Lambda is the regularization parameter which balances between simplicity and accuracy of the model. The figure shows the shrinkage of the regression coefficients W, as we change lambda from 0 to 1. We can see most of the coefficients are removed, where lambda is greater than 0.9. Only remained feature was, the minimum distance to the obstacles. We can predict the reward function of human expert through his demonstrations, but we cannot validate the accuracy of our method, because the ground truth of the human expert's reward function is unknown. So, for the test, we generated 5 trajectories from 5 ground truth reward functions, using deep reinforcement learning. The figure shows that our GP with L1 regularizer predicts the reward parameters well. We set up the experiment as follows. 2 obstacles were placed between the start location and the goal location of the mobile robot. This environment was intended to see the behavioral difference while the human experts controlling the mobile robot to navigate the start position to the goal position. This is the experiment video. Human expert demonstrations and the learned policies. We can see that trajectories between learned policies and the corresponding human experts are matched very well. We collected demonstrations of the 3 human experts. 3 experts have the robot driving behavior of aggressive, balanced, and conservative, respectively. 5 trajectories were collected per each expert. The trajectories of the trained policies were shown very similar behaviors to the corresponding human experts' demonstrations. We compared the proposed method with adversarial inverse reinforcement learning, which is one of the state-of-the-art inverse reinforcement learning methods. The trajectory generated by the proposed method successfully recovered the expert trajectory, while the trajectory generated by adversarial inverse reinforcement learning failed to achieve the target position arrival. Let us summarize the advantages of the proposed method as compared to the existing inverse reinforcement learning methods. First, we have presented an inverse reinforcement learning method that can cope with a small number of experts' demonstrations. Second, as we explained, other inverse reinforcement learning methods may be difficult to stabilize the learning process, while ours is stable due to our modularized approach with GP regression. Third, after training GP with selected features, the proposed method can predict the reward function without a learning process. Thus, the proposed method is expert data efficient. Finally, the proposed framework is modularized and so it can work with any kind of control, planning, or reinforcement learning methods as a policy. Thank you for listening.